So let's start with one concrete example, right? So enough with storytelling. So let's try to do one thing that is very famous, the problem of classification. So what is the problem of classification? This is a supervised problem because you have your labels. The only difference with the general case that we talked about is that the labels are integers. What does it mean? It means that your label could come from a few possible cases, right? For example, it could be 1, 2, 3, 4, till 10, right? It could be cat, dog, frog, horse, right? So your label is coming from a finite set of, say, integers. So a few countable cases, right? So when you have your label in this form, when it's coming from a discrete set, this is a classification problem. And usually we call it class 1, class 2, till class j, right? So cat is class 1, dog is class 2, frog is class 3, and so on, right? Now, every single data sample has its own class or its own label, and a typical data set that you're going to have is going to be of this form. For instance, when we think about image classification problem, which is one of the first problems we consider in machine learning, is of this form. So you have your first image and its label, right? You have your second image and its label, its class, and so on, right? So this is the data set that you have, correct? So this means that you go out there, you're going to capture images of cats and dogs, and then you, for each image, you're going to write, this was a cat, this was a dog, so this is the ground truth. You keep it inside one data set, right? Now, the question that you might tell me is that you talked about images to be vectors, cat and dog to be some labels, some numbers again, and how can I make this data set that I have made into that numerical form? I do know that most of you have the understanding of this, but just to make it very, crystal clear for those who are maybe less familiar with image processing and things like that, well, if you have an image, you can always write it down in form of array of pixels, right? So if I have this image, say this is an 8-bit image, right? And by 8-bit, what do I mean? I mean that I have a specific number of pixels. So your image, you can grid it into pixels, right? There are a few lines. So for example, 100 by 100, right? So they're going to be 10,000 in total different pixels, right? And every single pixel has a value which is shown by only 8 bits, right? When it's 8 bits, it's going to be either 0, 1, 2, till, what is the last value you could have? 255, right? You cannot show 256 anymore with 8 bits, right? And so on. So this means that every single pixel that you have is a number between 0 and 255, right? And if you have 100 by 100 image, this is the resolution of your image, you can show the whole image with one vector which contains 10,000 different values, every value between 0 and 255, right? So this is one image. So you can get your image, and then you can write it down in form, you can, instead of these pixels, you can write down the values, and eventually the image that you see is just collection of intensities, light intensities, proportional to those values, right? When, for example, this is absolutely 0, this means that this is complete black. If this is 255, this is complete white. And if this is anything in between, it's going to be gray, right? And the intensity of that gray is depending on the value, right? So that's one image. So you can always get your image and write it down in form of a vector. This is what I'm going to show by x. So the image to us is simply one vector x, which is collecting all of the pixels, right? And just to make it clear, I'm going to call it pixel vector, right? So the thing that I can do, I can take all of those images off my data set and replace their image pixel vector, right? So I can do this to the image. For the label, I can again do this by numerics, right? I could agree that I just make this agreement that When it's cat, I'm going to label it by 0. When it's dog, I'm going to label it with 1, right? If you have more classes, you just add more, right? If it's frog, I'm going to show it by 2. If it's horse, by 3, and so on, right? And now I can write down my data set, which was of this form, in this form, right? The first image is image of a dog. I'm going to get the image and put the pixel vector here, right? So this image is replaced by one very long vector. Every single entry between 0 and 255. And instead of dog, I'm going to write 0, right? The second one is cat, so I'm going to put the pixel vector, I label it by 1, and so on till the last image, right? Now, I have now one data set. This is a numerical data set, right? And I can do whatever I want with it, right? At the end of the day, I want to see the new image. I just convert it to the pixel vector. I put it inside the model. At the output, I'm going to see the right label. This is what I want, right? Cool. Now, this guy is the pixel vector. This is indicating that I have a dog. And if I have a new image, if the model gives me 0 or 1, then I can conclude what is the image, right? OK, cool. Now, this is the problem of binary classification that I'm talking right now about. So here I'm just thinking about cat and dog, just 2 classes. So I'm going to focus on this binary classification now. And when I have this binary classification, this means that the number of classes that I have is simply 2, right? So this is the most basic classification problem that you have. You cannot have a classification problem with 1 class, because then any image is that class, right? You don't need to learn a model, right? So you need to at least have 2 classes, right? Binary classification, this is the most basic classification problem. So this was one of the very first problems investigated in machine learning and AI. So people at some point thought if they can solve this problem, then they can solve anything. Well, yeah, it took a long time, but that was true. And the other thing is that any other classification that you have, you can always write it down in form of a sequence of binary classifications. We don't do it anymore nowadays, but people early days were thinking like that, okay? So what do I mean by that? Say instead of having only dog and cat classes, I have 3 classes, dog, cat, and a car, okay? I can still solve this problem by 2 binary classifications, right? How can I do it? I might say, okay, I have one binary classifier. It's going to decide whether this image is a cat or anything else, right? If it's cat, that's over, right? If it's not cat, if it's anything else, I'm going to get into another binary classifier, right? So that binary classifier is going to tell me, look, I mean, it knows that this is not a cat, right? So it's going to be either dog or car, right? So if it's dog, I'm going to label it 0. If it's car, I'm going to label it 1, right? So if you have 100 classes, you can still do it that way, right? So if we can solve this problem, we can solve those problems as well. But in practice, as I told you, we're going to see, we're going to come with more trickier approach, approaches to solve this problem, okay? So, but right now, we're just focusing on this binary classification problem, and let us just build the 3 main components that we have in the binary class in any machine learning problem. The first component was data, right? So we already have the data set, right? So the data set is in this form. X's are the image pixels. So if I assume that I have n pixels in total, then X is going to be n-dimensional, right? So famous data set for image classification is MNIST, right? And MNIST, every single image inside it is 28 by 28. It means that 28 times 28 is 784, right? 784 different pixels, right? So n is 784. If you have 100 by 100, it's going to be 10,000 and so on, right? And you can imagine, if you think about the nowadays images, this n could be crazy large, right? OK, so that's X, and Y is the label. This is a binary label. It's either 0 or 1, right? Cat or dog, car or plane, something like that, right? OK, so that's the data set. And the next thing that I need to do is to have a model. So what does the model do here? Or how should it look like? It should be a function, right? That should be a function. that function should have an input. What is the input? The pixel vector, x, right? N different pixels. So these n different values should go inside. How should the output look like? It's going to be a label, but what should it be? What is the label? 0 or 1, right? So if I want my model to match what I have in my data set, this should take the pixels, and as the output, it's going to give me either 0 or 1, right? If it gives me 3, this is not a right model anymore, right? Because I don't have that label, right? So I am going to just make a classification model, which some people call it classifier as well. I mean, just a term, in this form, okay? And you tell me whether this is a right model or not. So first, let's see whether it's working. How does it work? So I'm going to have n different pixels, right? I'm going to put these numbers here. Each of them is going to get multiplied with a weight. So the first pixel with its own weight, the second pixel its own weight till the last one. I add up everybody here, right? I add one bias as well. This z value here, what is it? Is it a number? Is it a vector? Is it a matrix? It's a scalar number, right? This is a scalar number. What could it be? Could it be minus 10? Could it be? It could be, right? If I choose, like, say x1 is 1, everybody else is 0, I put this w1 minus 10 times 1, plus, say, bias is 0, it's going to be minus 10, right? So it could be any real number, right? Correct? Everybody's cool? Now, I have this real number. This cannot be the output of my model because this is not the label that I want. The label that I want, it should be either 0 or 1, right? So what I'm going to do, I'm going to look at this z, and I decide whether I want to have 1 or 0 based on its sign, right? So if it is non-negative, I'm going to put 1. If it is negative, I'm going to put 0, right? Now, this guy y, what it could be? It could be only 0 or 1, right? If z is negative, it's going to be 0. If z is positive, it's going to be 1, right? So this y now is of the form of the label that I have. This now can be the output of my model, right? So this guy is now a model, right? So I have a bunch of weights here. Essentially, I'm just computing an affine transform because I get my x. I multiply linearly with my weights. I add a bias. And I get z, right? Z is this affine transform of x, right? And then after that, I'm going to pass it through this function, which is eventually this step function, right? Because if you look at this function here, if I want to plot y in terms of z, then maybe I do it here. If I want to plot y in terms of z, how does it look like? If z is negative, if I am here, y is going to be 0. If z is positive, it's going to be 1, right? This is a step function, right? So from 0, it jumps to 1, right? This is a step function. I'm going to show it by s, step s, okay? Now, this guy that you see here, this is what we call it perceptron, okay? And perceptron is the grandfather of the neural networks that we have nowadays. So I'm going to just show it compactly in this form. So I'm going to have a bunch of x's, right? They are getting multiplied with weights, added up to the bias, and then pass through this step function, right? This step you see here is the step function impacting on this calculation, right? And then the output is going to be either 0 or 1. This is now a right model, and I can use it to, do the classification on my data set. Everybody's cool? Great. So this is the model, and you might come up, first of all, we usually call it a linear classifier. The reason that we are doing, we call it linear because eventually the parameter z, which is going to finally decide what the label is computed linearly, right? So z is the one whose sign is going to specify the label, right? And that z is computed linearly. This is why we call it linear classifier. And I can write down this model compactly in this form. So starting from the input, every single x get multiplied to its corresponding weight, right? Then you add everything up. You add the bias. This is the thing computed as z for us, right? And then you just pass it through this step function. You check the sign, right? Now, if you look at this one, can I write it down compactly in form of vectors? What is this sum here? It's an inner product, right? So I'm going to write it down as inner product. If I call this vector w to be the collection of all weights, and then I put these x's all together inside the pixel vector, right? This is the inner product of weights with the pixel vector, right? So I can write it down in this form. I can write it down as the step function applied on the affine transform of the pixel. Basically, you get your pixel, you do one affine transform on it, you get a value, you check the sign, right? That's your model. Questions? No question? Great. OK, if you got no question, now a few things here. First of all, what is the hyperparameter here? Do I have any hyperparameter here? Well, this is not the classic hyperparameter that some of you might have think of. But yes, I have hyperparameters here as well. I mean, who told me to choose a step function when I want to change that z value to 0 and 1? Can't I choose another function? Yeah? I could choose any function which takes a real value and give me 0 or 1. That is a possible thing, right? So I chose to have a step function here, right? Who told me that I should have a bias here? I could do no bias, right? I could just forget about the bias. So these choices are things that I have done, right? But I need to do them in order to be able to write down the model, right? So these are hyperparameters. Having bias is a hyperparameter. Choosing this step function is a hyperparameter. And many other things, right? So you can think about the choice of the step function and also the affine transform. These choices, you can think of them as the hyperparameter, right? And once you set them, now you have your perceptron written, right? You could have a perceptron without bias. You can have a perceptron with bias. This is your choice, right? Now, once you have done the choice, then you're left with a bunch of weights to learn. For instance, in this particular perceptron, how many weights do I have? Go ahead. N plus 1, right? Bias as well, right? So I have n plus 1 different weights. All the weights, W, and the bias that I have. These are all learnable parameters, right? At the end of the day, I want to find those weights and the bias in a way that any image goes in, if it's cat, the z value is going to be positive. If it's dog, the z value is going to be negative, right? This is what I want to see. Everybody's clear? Right? So these are learnable parameters. These are the things that I'm going to learn through the training, which we are going to talk about shortly. Okay? Cool. So if that's the case, if everybody's clear, now one thing that I would like to do here is the geometric interpretation of the classification here, because this is the most classical thing you always see in any textbook, any presentation, anything. So many times you see when people want to talk about classification, they immediately write down two-dimensional coordinate, put one line, and say this is classification, right? And I guess some of you might have a very clear idea about that, but I just want to make sure that everybody is clear, okay? Now, what you have here, you can always think about this as a kind of linear cut of the n-dimensional space that you have. And in order to understand it perfectly, I'm going to stick to the two-dimensional case. Now, I'm going to think that my image has only 2 pixels. This is dummy, but this is the easiest way that we can describe it, okay? So I have only 2 pixels inside my image. This means that my pixel vector is going to be 2-dimensional. These 2 pixels, each of them has its own weight. they are going to get multiplied with those weights. There is one bias is being added, right? Then you're going to get a real value. Based on that real sign of real value, you're going to decide whether this two-dimensional image is cat or dog, right? Everybody's cool? Okay, so this is the one which I want to consider. Now, if I open up the perceptron expression, it's going to look like this, right? This is exactly what I told you in words. So I'm going to get the weight of the first pixel multiplied with the pixel, weight of the second pixel multiplied with the pixel, the bias, and I check the sign, right? If it's positive, label is 1. If it's negative, label is 0. Cool? But since I have a two-dimensional case, now I am able to plot everything in two-dimensional space. So what do I mean by that? Let's think about this line. This is the line z, which is computed out of multiplication of every pixel with the weight and adding up with the bias, right? Okay? Now, if I think about this as a line, this guy, z, as a line, in a space with x1 and x2, right? So the coordinates are x1 and x2. If I want to plot this line, how does this line look like? Let's do it once together, and then I guess it's going to get very clear for everybody. So I do it here. Let's say that W1 is 1, W2 is 1, B is 1 as well. Okay? Now, if I want to draw that line, that z is going to be x1 plus x2 plus 1, right? And I want to draw this line, x1 plus x2 plus 1 equal by 0. So I'm going to say that I have this two-dimensional space. Here is x1. Here is x2. Okay? And now I want to find out the line. Okay, I'm going to remove this z here. I want to just plot this line. x1 plus x2 plus 1 equal by 0. What do I mean? I want to plot the points x1 and x2 which satisfy this equation. How can I do it? Okay. I'm going to write down x2 in terms of x1, right? So I'm going to say, since this is 0, x2 is going to be minus x1 minus 1, right? Correct? And now, if you look at this one, so you're going to just put x1, for example, 0, right? x2 going to be minus 1, so here is minus 1 when x1 is 0, so this is 1 point. The other point is when I put x2 equal by 0, then x1, if I put x2 equal by 0, x1 is going to be minus 1, right? So this is the other point. Everybody's cool? Now, any point on this line which is passing through these points, right? These 2 points, right? Any point, if I just take any point here, and I look at the value of x2 and x1 on it, right? Then when I put it here, it's going to be exactly 0, right? Everybody's cool? Everybody's clear? So this is the line that x1 plus x2 plus 1 is 0. Now, what's going to happen if I look at one point here? If I take 1 point here, if I have 1 point here, this one has x1 and x2, right? What's going to happen if I put this x1 and x2 inside this equation? It's not going to be 0 because this is not on the line. But what's going to be its sign? It's going to be positive, right? Say, for example, this point is 1, 1. You put 1 plus 1 plus 1 is going to be 3, right? So any guy here going to have positive sign, right? What about the points below this line? All of them are going to have negative sign, right? So that means that if my image is here and it passes through the perceptron with those weights being 1, 1, bias being 1, right? This is going to be classified as 1, right? The label is going to be 1. If the image is here and it passes through the perceptron, the output label is going to be 0, right? So you can do it in general case. So you could say in general I have a bunch of weights and a bias. It's going to be always one line. If you set that line equal by that expression equal by 0, this is going to be one line in x1, x2 dimension. So here x1, x2 is showing your image. This is your data dimension, right? And okay, sorry. And then what you can say, anybody on this line is going to be 0, gonna give me 0 as the output, but anything above it is going to have positive sign, right? When the sign is positive, it means that the label is going to be 1, right? And anything below it is going to have negative sign. Any point below this line, when passes through perceptron, is going to have negative sign for its z value. And then its label is going to be 0, right? So what you can think about this linear classifier, this perceptron, is that this guy is essentially always drawing one line and then looks at the data that it has. If the data is above that line, it's going to classify it by 1. If it's below that line, it's going to classify it by 0, right? Everybody's clear? So you can always think about this. So if you are given with this data point, say this is one two-dimensional image, two-pixel image, sorry, then this guy is going to be labeled as 0, right? Because this is lying below the line described by your perceptron, right? Anyone below is going to be classified as a dog. Anyone above is going to be classified as a cat, right? Everybody's cool? Now, what do you have as the choice for training? What do you do when you train your model? What is your degree of freedom with this line? You have 3 degrees of freedom, that's right. And what happens when you change those degrees of freedom? You change the line, right? So you have your data. When you play with those weights, W1, W2, and the bias, you are just shifting this line, rotating this line, right? This is the degrees of freedom that you have, right? So eventually, if your data looks like this, all dog images are here, and all cat images are there, then you play with the weight side that this line dropped exactly between these two groups, right? And then you would say, okay, I have done the right choice based on the data that I have. Yeah? And what you hope is that any new cat image, any new dog image exactly lie in those regions, right? Everybody's cool? You got the idea? Okay, cool. Now, just a bit of history here. The idea of perceptron was introduced in 1957 by Frank Rosenblatt, and he was able to implement it with a huge machine. You can imagine at that point of time it was really analog implementation, but he was able to actually learn many binary functions, right? And this was a kind of breakthrough. But he wrote one complete survey on 1958 on describing how this perceptron is going to be a kind of, a road towards artificial intelligence, like building machines that are able to decide and think. But the original story comes a bit earlier. So it was 1943. Makla and Pitts. I mean, Pitts was a mathematician. Makla, he was mostly working on psychology. And he was interested to understand how does the brain work. And then they came up with this sort of computational model for neurons. So they said, like, how does the neuron work in our body? How do we feel something when it touches us? Well, there are some synapses on our body in the neurons. Those synapses, once they get excited, they're going to just generate some signals, right? And those signals are going together, are going to add up with some weights, right? And then after adding up, there is a threshold there. If this add up passes the threshold, then you are going to feel that. If it doesn't pass the threshold, you don't feel it, right? And then the question was that, the main question that they were thinking at that point of time was that, okay, why I feel it right now, but if you keep on doing to me at some point, I don't notice it anymore because those weights are somehow pushing up, right? So the threshold, everything is changing. Is it really the case? Well, we don't know, right? At least I don't know. But the point is that it was a right computational model. It was a kind of model which was describing the thing that you see, right? And this was somehow, the paper that they have written in 1943, even now is a bit hard to follow what they have done, right? But the key point was that they came up with this kind of computational model for the neuron. And Rosenblatt, eventually what he did was that if this is really how the neurons work, and eventually we as intelligent creatures, we are we consist of lots of neurons. Probably if I make those mathematical models and put all of them together, then they are going to somehow do whatever I can do, right? And then he started with the classification problem with lots of those tiny perceptrons, and he was able to do something. And then he said, probably this is correct, right? But nobody followed this up due to some reasons up to the point where, again, the idea of neural networks started to be a thing, okay? But the idea, the introduction of perceptron was a great achievement in this area. But for us, perceptron is simply a model, right? A mathematical model, always. Just a bunch of weights, multiply with the input, give you one linear classifier, right? And it's not different from polynomial or anything else, right? Okay, so now, everybody's clear about the perceptron idea, how it does the classification? Okay, cool. Now, looking at the problem that we have, we already know what is the data set, right? The first component is clear, image and its label. We do know the model, so we chose the perceptron to be the model. We chose it by our own. This was our choice. But then once we chose it, now we have a bunch of ways to learn, right? And then the question here is that how we can learn those ways. Well, we need the third component, which is the loss function, right? So what should I choose as the loss function, right? So you might say, OK, I can just use this square error that you told us, right? I look at the output of the perceptron. I compare it to the true label, right? If it is 1 and the true label is 0, then I just subtract them, make them a square, right? Well, you can do it. You can also do the error indicator. That is also a case. Like you look at the output of the perceptron and see whether this is exactly what you have in your data set or not, right? If it is, then you're going to keep it. If it is not, then you're going to change the weights, right? So this is the error indicator. We can go for more smart approach based on the KL divergence. I don't expect you to know what it is, but we're going to end up with the cross entropy. We see it later, okay? But there are better choices of loss for this model, okay? And for now, we are going to stick to the one which was done by Rosenblatt. So Rosenblatt eventually, when he proposed this architecture, this model, he also thought about the error indicator. He said, like, I'm going to look at the output of the perceptron. If this is exactly the thing that I have in my data set, then there is no error. If they are different, then I'm going to say error 1, right? So it's eventually the error indicator, right? And now the only question was that whether we can come up with an algorithm which we start from the data, we just give it into our model. So we choose the weights and bias randomly, okay? We just give our data or images into the perceptron. We look at the output. We compute the loss using the true label. And out of that, we conclude what we're going to do with the weights, right? How we should change the weights up to the point where we have no error happening. Yeah? And this is the perceptron algorithm, which we're going to talk about this. But now, before, OK, I think this is just kind of extra description of what we are doing in this error indicator loss. So this is your perceptron when you give your image into the perceptron. This is one image from your data set, right? So xi is one of the images that you do know whether this is cat or dog. Once you get the output from your perceptron, that output is either 0 or 1, right? But can that output, is that output necessarily the label you have in your data set? Well, no. If your model is working fine, it's going to be the same thing. If it is not, it's going to be a different thing, right? And then the loss that you are computing is that you basically compare this output, y hat, to y, the true label that you have. And when they are different, you're going to declare an error, right? So I wanted to give you an extra graphical point here. One thing else, I'm showing this y hat here, right? So y hat is the output of the model, right? This is not the true label that you have inside your data set. So y hat is an estimate of y, right? So you saw your image, you estimate it's a cat, then you check in your data set, you see that no, it was a dog, right? Now you have an error.